I'm looking for you to be very engaged at the presentation.
Today we are going to talk to you about protein extraction optimization from canola and rapeseed. A little bit about canola and rapeseed is that they are members of the Brassicaceae family, and worldwide it is one of the most common sources of vegetable oil, as well as the second most common oilseed crop after soybean. So canola is just GMO rapeseed that is genetically modified for low uric acid, which is an anti-nutritional factor that they removed. And canola just stands for Canadian Oil Low Acid. It's being considered as a protein source because it is currently being utilized, the oil is, for biofuels and food uses. However, from the oil extraction, there is left a proteinaceous press cake that is currently being utilized for animal feed. However, the protein has high potential for food uses. Some of the benefits are that it has a short growing season, so it allows it to be a cover crop for a 2-cycle rotation with corn or soybean. It's non-allergenic, it has potential bioactive properties, and it has promising functional properties as an ingredient as compared to other plant protein sources. And if it's produced with no solvents or chemicals, it can be a functional clean label ingredient. The two major proteins that are present in canola and rapeseed are cruciferin and napin. Cruciferin, being the larger of the two as a globulin, is comprised of 6 subunits that are connected with disulfide bridges, whereas on the flip side, the napin is smaller and it is comprised of 2 polypeptides that are connected with a disulfide linkage. The cruciferin makes up about 60%, whereas the napin only makes up about 20% of the total protein in canola. The cruciferin is salt-soluble, whereas the napin will be water-soluble. And on the reverse side, cruciferin will precipitate at pH 4 to 7, whereas napin will precipitate at alkaline pHs around 10 or greater. To extract the protein from the oil seeds, the first method is to extract the oil, which is done with a physical means by a screw press, which is shown here in the box, or a hydraulic press under hot or cold conditions. Then the residual fat is extracted with either hexane or supercritical fluid, and then the defatted meal is reduced in particle size with a mill, and then there are 3 different extraction processes that we had talked about in class, being saline or salt solubilization, alkaline, or membrane filtration. In alkaline protein extraction, this is the most common one that's seen in the commercially produced like soy protein isolate. And with soy protein, the proteins are solubilized at pH 7.5, whereas on the flip side, for canola, the proteins are soluble at more alkaline pHs from 10 to 12. And then both of them isolate the protein by dropping the protein or the solution at the protein's isoelectric precipitation point between 4 and 5. However, the high alkaline solubility will give some denaturation to the protein, which will affect structure and function for food applications. And additionally, it can give off flavors and odors for a bad sensory of the protein ingredient. For the salt extraction, we had also talked about this in class. By increasing the ionic strength, we can solubilize more proteins to isolate them from the meal, and then we can precipitate them by oversaturating. And this can help to overcome some of the denaturation or off flavors that are produced with the alkaline extraction. However, when we do this, the removal of salt is very crucial, and that can pose some costs for the membrane and filtering, as well as the washing steps needed to remove the salt are not efficient or sustainable. On that same note, looking at sustainability, currently in the industry, to get optimum yields, they are doing 5 to 10% solids and using a lot of water, and they'd like to move more to like a 15 or 20% to increase water efficiency and be a more sustainable process. Therefore, understanding the optimum conditions to produce a protein ingredient is important to have a protein that is highly pure, functional, and can be used in various food applications, which brings us to our two manuscripts. The first manuscript, we're going to be looking at canola protein extraction efficiency that's affected by total solids, salt solubilization, or the solubilization pH. And then for the second manuscript, we're going to be looking at the effect of pectinase enzyme at just 1 pH and its effect on total solids.
So in the first manuscript, we looked at the study of total dry matter and protein extraction from canola meal as affected by pH, salt addition, and use of zeta potential or turbidity analysis to optimize the extraction conditions. So the objective of the first study was to determine the optimal solubilization and precipitation pH, the ionic strength, and the total solid conditions on protein extractability. And the four hypotheses that were developed were protein extractability in the alkaline method of extraction will be increased with the addition of salt, and then more alkaline solubilization conditions will increase protein extractability. Lower precipitation pH, so from 4 to 6, would increase the protein extractability, and then more total solids would decrease the protein extractability. So the defatted canola meal was provided, and it was measured to have a 34.5% protein, and then 3 methods of extraction were performed. The alkaline and saline extraction were done at 5, 10, and 15% dry matter, using a pH level of 10, 11, and 12. And then in the saline extraction, 0.01, 0.1, and 1 molar of sodium chloride were utilized to get the saline protein extract. And then in the alkaline extraction and acid precipitation, it was done at 5% dry matter and at pH 12. And then from there, the protein was precipitated from pH 2 to 11. So the proteins were analyzed for crude protein, protein profiling, and zeta potential for the measurement of surface charge. And the resulting protein extractability can be seen in the graph displayed. So it was separated by the percentage of canola meal at 5, 10, and 15%, and then categorized by the pH level of pH 10, 11, or 12. And these solid bars represent the total dry matter extractability, which is defined as the amount of weight in extracts over canola meal. And then the striped bars represent the protein extractability, defined as the nitrogen in extracts over the weight of the canola meal. So we can see that at a higher pH level, there's an increase in protein extractability. So there was about a 2.5 times increase from pH 10 to pH 12. However, there wasn't any effect in protein extractability for the total percent dry matter. When understanding the effect of salt concentration and pH on protein extractability, this was again categorized by the different pH of 10, 11, and 12. And it was, on the x-axis, you can see it's from a canola meal percentage of 5 to 15, and then a predicted salt concentration from 0 to 1, where the protein extractability percentage is seen as darker the shade, the increase in extractability. So we see that at pH 11, the most optimum conditions are at 0.9 molar sodium chloride, and at 8 to 15 canola meal percentage solids. And then in pH 10 and pH 12, you see similar optimal conditions at 1 molar sodium chloride and 5% canola meal solids. And then I'd like to point out, so when salt was added to the pH 12, without salt, there was a 58% extractability, and then we saw a decrease when salt was added to a 43%. So with the effect of pH on surface charge, we see that there is a decrease, as pH increases from 2 to 12, there is a decrease in zeta potential from a positive charge to a negative charge, crossing the isoelectric point between 4 and 5, and reporting a minimal net charge at 4.3. In the SDS-PAGE protein profiling, we see that in non-reducing conditions, there's high amounts of polymerization, which then disappears in reducing conditions, so that's indicating that there is presence of disulfide bonds. And polymerization in canola meal indicates that there's possible use of heat in the oil extraction. So that was without the salt, but then when with salt added, we can still see that, again, there's high amounts of polymerization. And so the cruciferin bands are more prevalent in salt extraction samples compared to the non-salt. So drawing conclusions from this manuscript, we see that the solid content had no influence on protein extractability for alkaline extraction, and the salt addition lowered the extractability at all pH values. So the highest protein extractability from the isoelectric precipitation was at 4.3, and then the alkaline extraction at pH 12 at any meal concentration was observed to have the highest protein extractability. So then, linking this to the second paper that Rachel will talk about, the alkaline extraction at pH 10 may increase protein extractability and produce a less denatured protein ingredient with the use of enzymes.
So for the second manuscript, we are looking at the impact of total solid content and the extraction pH on enzyme-aided recovery from protein from defatted rapeseed press cake and the physiochemical properties of the protein fractions that are isolated. The pectinase enzyme is of interest for increasing protein extractability, as protein may be bound within a polysaccharide cell wall, and the pectinase can help to break down the cell wall to increase the affinity of the protein to solubilize within extraction to be isolated. Therefore, the objectives were to determine the effect of solid content on protein recovery during combined enzymatic treatment and alkaline extraction of rapeseed protein, and the hypothesis was that the use of pectinase enzyme will increase the rapeseed protein extraction efficiency at higher percent solids to limit the amount of water consumption during production. And the second objective was to investigate the impact of extraction pH and isoelectric precipitation on protein recovery and solution behavior of the protein concentrates. However, the hypothesis is that the alkaline extraction and acid precipitation will reduce protein solubility due to partial denaturation. To test this, the rapeseed press cake was already given and the residual fat was removed with supercritical CO2 extraction and milled. From the defatted press cake, there was enzymatic treatment, and then there was just a water treatment done at 40 and 20% solids. And then from there, for both of the treatments, there was alkaline extraction and water extraction, or reference, in which was performed at 20 or 10% solids. And then from there, we have the alkaline extract, which I will refer to as pH 10E, E for extract, or pH 6E, E for extract for the water extracted ones. From the alkaline extracts, they did isoelectric precipitation, and they obtained a supernatant and the precipitate. The supernatant will be referred to as pH 10S for supernatant and pH 10P for precipitate. The protein extracts were analyzed for purity, yield, composition, solubility, and zeta potential, or surface charge. Looking at the protein extraction results, we can see the difference for treatment solids at the top as well as the extraction solids. And then we're looking at the difference in pH 10 extraction versus pH 6 extraction. We can see from this that the enzymatic treatment improved protein recovery at pH 6. However, the enzymatic treatment the pectinase enzyme had no effect on the alkaline extraction at all of the different solids. The percent solid content during the enzymatic treatment had no effect on pH 6 or water extracts at 10% solids. However, at 20% solids, we did see a decrease in protein extractability. Looking at the protein precipitation results, from the graph on the left, you can see the amount of protein that was precipitated compared to the amount of protein in the meal. And we see that we have lower yields that are around 30 and lower. And then on the right side, we can see the amount of protein that was precipitated compared to the amount of protein that was extracted. And we can see that, again, it's lower than we would like, and it's around 60% and lower. And we see that the enzyme actually decreased the amount of protein precipitated in each case. Looking at the SDS-PAGE or protein profiles of these, looking at the comparison of the pH 6 and the pH 10 extracts, there was no selective extraction of major proteins that occurred, meaning that at the alkaline pHs we still saw napin and cruciferin bands as well as in the water extracts. The napin, so looking now at the protein precipitates versus the supernatant that it was precipitated from, the precipitates, the napin did not precipitate at pH 4, as well as we still see a large abundance of cruciferin bands in the supernatant that were left. Looking at protein, carbohydrate, and ash for the protein precipitates, as well as the water-soluble or pH 6 extracts, we can see that there is a higher protein purity for the precipitates due to the isolating step for the proteins, which can also be backed by the amount of carbohydrates that we see in the pH 6 extracts or the water-soluble extracts, again due to a lack of isolation. And for the protein precipitates, we see a higher ash percentage due to the addition of salt and pH adjustment. Looking at solubility, we see that at pH 4, there is decreased solubility as expected because of the decrease in, or close to the isoelectric precipitation point of cruciferin. And then there is lower solubility in the protein precipitates compared to the water extracts due to partial denaturation. Then looking at the zeta potential, this matches the same trend that we saw that Jason talked about, that at pH 4 there seemed to be a positive charge on the proteins, and then for the pH 10 precipitates, and then we saw a more negative charge for the pH 10 precipitates at pH 8 compared to the protein extracts at pH 6. The conclusions from this paper were that total solid content and enzymatic treatment had no effect on the alkaline extraction. However, enzyme-aided water extraction at low solids did increase protein extraction efficiency as compared to each other. However, the water extracts were still lower than the pH 10 or alkaline extraction. And due to the difference in partial denaturation and possible influence by carbohydrates in the water extracts and the protein precipitates, we saw different functionality as far as solubility. The main takeaways from both of these papers is that the extraction efficiency is increased more at pH 12 and that the total solid content does not have an effect on protein extractability within the alkaline precipitation method. The salt addition and alkaline extraction did decrease the extraction efficiency, and furthermore, the alkaline extraction causes protein denaturation and polymerization. Some critiques and improvements that we have about these manuscripts, starting with the first manuscript, is that they did not display their data very well for their discussion to understand what their conclusions were, and their salt influence on pH 10 and 12 seemed to be the same figure, as well as there's no proof or effect of denaturation on structure and function. For the second manuscript, in the discussion, they talked a lot about results that they did not report or display, and they could have done surface hydrophobicity to help their assumptions about their solubility and zeta potential data. Both of the manuscripts made conclusions that did not match their statistics or data shown, and they did not relate structure to function. They made a lot of assumptions about what was happening, and the zeta potential did not give any novel findings. Furthermore, a suggestion that we had was that utilizing a desalting step and a drying step would help to validate their structure and function work that they had presented. Thank you for your time. We will take any questions.
Okay, good. All right. I have lots of questions, but I'm going to give you no questions. Anybody?
Lucy.
Do you have any theories onto why salt didn't help with protein precipitation?
Did you have one first?
I'll just that it's. No, go for it.
No, Jason, tell us a little bit. Did they test different? They tested different salt concentrations.
Yeah. So basically, well, we can see that the cruciferin is salt soluble. So then there's going to be like a difference in how much is remaining from the when it is reduced. Am I getting at that correctly?
How much is remaining when it's reduced?
In the SDS-PAGE?
No, don't worry about SDS-PAGE.
Okay.
Before that, when they're
Okay.
extracting, do you think that the salt concentration they tested was adequate?
I mean, we can see that as you increase, and like, so my biggest question was, okay, so if we're gonna go like above 1 molar of sodium chloride, like obviously you see that as you're increasing the concentration, especially in like in the pH 10 and pH 12, you see that there's like better extraction. But as you increase it, it could potentially that's when you run into the
Opposite effect, right? Are you
Yeah.
searching for salting out?
that's the word.
Instead of solubilization, mostly precipitation?
Yeah, that's what I was going.
Yeah. So what was the concentration that they looked at, the range? Did they start it as low as, can you go back?
Yeah.
to the figure?
They started with 0.01, and then, so this is where the figure is kind of interesting. So they said they were doing it
Did you
at,
want this figure or
This
the?
is the only one on salt, isn't it?
Yes.
they said they were doing it at 0.01, 0.1, and 1, but then they have all these ranges between, which they did not do. So this is more so like, this is what's going to give you optimal conditions.
So they actually found the highest extractability at 0.9?
So in the pH 11, it was going to be from 0.4 to 0.9, but then in pH 10 and pH 12, it was at past 9.9. It was all the way at 1.
So I can fill in a little bit here is that they only tested those 3 protein concentrations and then they ran a regression to get these as an estimated amount based on different solubilities. So they didn't actually see the optimum or test the optimum conditions, they only assumed.
So they predicted without actually running extractions with salt?
Yes.
They did not use salt.
No, they did use salt, but they only used it at 0.01, 0.1, and 1 molar.
So that could be a big flaw in their system.
Yes.
Other question?
Becky?
So based on what you've learned from these 2 studies, what do you apply to industry and what would you recommend to them to optimize?
So the biggest thing that I would take away from both of these manuscripts is actually the effect of the protein within the meal is because in the first manuscript, if we were to jump to the SDS-PAGE, we see that even the canola meal has high polymerization, which could be due to denaturation within the oil extraction. But then with the second manuscript, they obtained the press cake that was, oh, sorry.
I don't see that. Where's the meal? Where's the polymerization in your meal?
Well, just the breakage of the disulfide bonds to give us our cruciferin and our naphthalene peaks. So this
that's
is
not
under,
polymerization because the nature of the protein is it is present as subunits associated via disulfide linkage.
yes.
So they are not polymerized due to processing. They are just naturally polymerized. So when you run it under reducing, same with soy. Soy
Mhm.
protein is naturally polymerized. So Then when you reduce it, then you see the individual subunits. Whereas at pH 12, you can obviously see the polymerization. Even when you reduce it, you still have some speed indicated that there was high level of polymerization, not only due to disulfide, but to other types of covalent bonding.
Okay, so I stand corrected. I'll finish my quick thought was that utilizing the conditions under like the supercritical fluid compared to the hexane extraction and the hot pressing versus cold pressing could have an effect with solubilization. And I also believe that it ends up being for industry a balance of how much money versus how much yields. So if they wanted to produce a highly functional ingredient that wasn't denatured, so had high solubility for their application, then they would want to use less harsh conditions, which could result in the use of different solid contents or lower pHs, but they're also going to get lower yields. Whereas on the flip side, if they're using it for like a baking or emulsion and they want that denaturation, that could also be applicable. I would also think that investigating the salt solubilization or membrane filtration could be a different step to look at depending on their food application. Yes?
Would there be any interferences from the hydrolysis product that were generated due to the enzyme effectiveness?
I'm sorry, I didn't hear
The
you.
hydrolysis products that were generated due to the effectiveness treatment, would there be any interference with the proteins or any effect on the results?
Yes, so the enzyme that was used wasn't hydrolyzing the protein, it was hydrolyzing the pectin. However, with the lower molecular polysaccharides that are produced from that, there could be higher affinity for interaction between protein and polysaccharides, which could affect the results that we saw as far as solubility and zeta potential. I think further investigation would have to be done to make that firm conclusion, though.
How did they prove that the enzymes actually worked and broke the cellulose? Did they test that?
They looked at the amount of lower or like monosaccharides that were present before, so in the meal, and then they looked at the amount of.
Was it a big difference?
They did not report that data explicitly, but they did say that there were larger amounts of monosaccharides present after.
And again, this could be another fluke because what do you think they could have done? This is a question to everybody. To prove that the enzyme actually broke the cellulose material and released the protein. What could they have used in terms of analytical technique that might show whether or not the enzymes actually broke cellulose and released embedded protein?
Protein content before and after, or any test which shows an increase of certain characteristic of the protein?
Well, obviously they didn't see a change in protein extracted. Microscopy. They could have done CLSM, and they could have stained, and they would have seen where the protein is and whether the cellular material would actually work.
Quick comment about that is that the manuscript I presented on, the manuscript that they did before this one, was the look at different enzymes, and they did do microscopy.
Oh, did they refer to it?
Mm-hmm.
Did they show that it did break the cellulose?
They did, but they utilized it under like optimum conditions for the enzyme, whereas for some reason in this paper they did not repeat the same conditions.
Well, then everything is not.
Yeah,
So back to square one.
back to square one. Another fluke.
Okay. Any other question, my friend?
Yeah, so for this slide, with increasing the pH, there was more polymerization. But when you back to the slide, with increased pH, it's actually decrease of the polymerization. Why is that?
Oh yeah.
this is without, and the other one is with
With salt, yeah.
The intensity.
so the presence of salt. With and without presence of salt. So with presence of salt, what effect you just said could have happened earlier with high salt concentration? You said it earlier in the first question. With higher salt concentration, you could get salt out.
Yeah.
Due to polymerization. Go back a little bit.
Oops.
No, one without the salt.
Yep.
It seems to me here there's a problem with their job.
Yeah.
They did say that they loaded based on protein concentration, but you don't see polymers, you don't see monomers either. So, yeah.
Both of the gels in the manuscripts weren't great.
Huh?
I said both of the gels in both the manuscripts weren't
Yeah.
great.
So I have a question. How was surface charge used to optimize extraction yield? It was one of the objectives of the paper.
So, looking at the zeta potential results, which I went the wrong way, I think that their objective was to utilize this to determine the isoelectric precipitation point. So if they were precipitating the protein at the proper range.
And then they found where the isolated point should be.
Yes.
Okay. In the hypothesis, why do you think that greater solid content will decrease the yield? Was that a hypothesis they made?
It was one that we had extrapolated from their introduction. They said that at higher solids, there's less interaction, or it's harder for the meal to fully
Solubilize? So the water is
Solubilize.
not enough
right.
to solubilize the protein?
Yeah.
But they only went to 15%. They didn't, so they made, either you or them made a general comment that solid content does not impact extraction yield. It did not impact up to 15%, but if they did 30%, it could have impacted.
Yes.
So that was just the way they state that. And then, can you go to your solubility slide? And this is more for the entire class, really. We're done asking, we asked a lot of questions, but to me here, there is something very obvious, and they didn't make really a discovery in terms of solubility. Can you guess what I'm talking about? At pH 6, the extract had higher solubility than pH 10.
Am I allowed to answer?
Huh?
Am I allowed to answer? Or no?
You are allowed to answer.
If we only utilize water to do the extraction, the only amount of, or the proteins that will be in that are water soluble, so
Oh,
obviously
really?
they'll have,
Yeah.
Yeah.
So it's like you extract them as water soluble, so obviously they're going to be soluble. So this is, I think what I like about this exercise of presentation is to help you when you write your own papers. Is like you want to really present something obvious, or you want to present something groundbreaking. This is just, sorry, I'm going to say BS. I mean, really? Okay, it's water soluble. So what? Okay. Yeah, let me see if I have anything else here. So when they put that much amount of salt, did they do any dialysis at all, Jason?
No, that I remember reading about.
Okay, so they didn't. So what would that be potential problem?
Yeah, I don't.
Yeah, yeah.
the potential problem could be that the salt concentration given whatever the amount, even at dilute, can add ionic strength that can give false reports for solubility as well as zeta potential, because the salt will either add ionic strength to increase or decrease the charge, as well as it could decrease depending on the concentration.
Decrease, yeah, can shield the charges or can interact more with water and impact the functionality of the protein. So that is another major issue there when you're using that much salt and then you end up leaving the salt in your extract. But I didn't see that they tested, the first paper at least did not do any functionality testing, did they?
Just the zeta potential.
So they,
No functional, just
no functionality, they just were looking at the yield. That was their major. Okay, well, thank you. And when you're done, let's put this here. I'll give you a moment to fill this up and be done with it. We're all done? Okay. All right, I guess this was the last slide from last week. So we were talking about the globulins in oil seeds, and they are classified into legumin and viscillin. In soy specifically, legumin is glycinin and viscillin is beta-conglycinin. That is for soy specifically. And we talked about the difference between 11S and 7S, or we talked about what S meant. Can you remember? Do you remember what that means, that value?
Sedimentation.
So sedimentation coefficient. So does the higher number indicate a larger molecule or a smaller molecule? or a molecule that would sediment easier or will remain in solution longer upon a certain centrifugal force. Yes, Becky?
Larger sediment, or larger number of sediments lower?
So is it a lower molecular weight or a larger molecular weight, you would say?
Larger.
Okay, so if it's larger molecular weight, then it sediments faster. I think it's confusing because the definition of sedimentation coefficient is the ratio of the speed of sedimentation to the centrifugal force. Okay, so if we have a constant centrifugal force, the molecules that are larger will fall out quicker than the molecules that are smaller at the same centrifugal force. So that means when you have a bigger number over a smaller number, then you will get a bigger S, or the ratio of speed to the speed of sedimentation to the centrifugal force will be a bigger number, therefore a larger molecule will sediment more than a smaller molecule. Okay. Hope I did not confuse you, but think about it and then you will find that true. Okay, so these molecules, or these globulins, are present naturally as oligomer. That means they are associated with several subunits are associated together. And by nature, globulins have over 40% of their amino acid as hydrophobic amino acid. So they have large percentage of hydrophobic amino acid. They also have a large amount of acidic amino acids, especially aspartic acid. So that gives you a balance between hydrophilicity and hydrophobicity. And we talked about the homology. There's large homology in the sequence. That means similar sequences within these proteins and even across species. So I talked about last time that if you are allergic to peanut, you might have cross-reactivity to soy just because of the similarity between the amino acid sequences. And that's why when we say pea protein is non-allergenic, let's not be very happy about it for a long time. And then we talked about the ratio is different between different varieties and also among different species, the ratio of 11S to 7S. And because they are different in structure, they will impact functionality differently. So different ratios will impact functionality. So, yeah.
So if you are allergic to pea and you have a reaction to soy, then does that mean that that reaction will happen every time? Or just because, wouldn't you then, if you have a cross reaction to soy, wouldn't you then be allergic to soy?
Yes.
Okay, so
Yeah.
it's just...
So you have to eliminate soy from your diet as well. Unless, here's the thing, so you might have some sequences that are similar, but not every individual is allergic to the same sequence. So some people are allergic to a unique sequence that might not be in soy, but be in pea, while others might be allergic to a sequence that is present in both. So it's very individual based. Okay. So for legumin, we have a sedimentation coefficient that, depending on the variant, it can vary between, or genetic variant, I want to say, it can vary between 10.8 to 14.6, but the average is 11S. That's the 11S is an average number. The molecular weight also varies between the different subunits. You will see, we'll talk about there are different subunits that can form the legumin polymer. So that would make the molecular weight vary as well between 300 to 400 kilodalton. So it's a large, really large polymer. So unlike whey protein, for example, that exists as a monomer or a dimer or an octamer, they have much lower molecular weight than this as a protein. We said they are high in acidic amino acids, but also they're high in arginine, which is a basic amino acid. In general, they are low in sulfur-containing amino acids. So in general, legumes are deficient in methionine, for example, which is a sulfur-containing amino acid. In general, they're not glycosylated, but they might be glycosylated, but really less than 1% of saccharides in them. An example of a legumin is the lupin that could be glycosylated. So if we look closer at the molecular structure, which is really important to understand because it leads you into how they associate and how they dissociate and how that might impact their solubility and functionality. So molecular structure of the 11S, basically it's composed of 6 monomers. Okay, and this can get confusing because when you say monomer, you think a monomer is one subunit. But I'm going to make it confusing and I tell you no. A monomer is 2 subunits, in this case, linked by a disulfide linkage. So you have the acidic and basic subunits. Acidic and basic subunit are linked together by disulfide linkages, forming a monomer. And then the acidic is the bigger circle here, is the larger one, so it has around 60 kilodalton, whereas the basic, it's larger, it has 35 kilodalton, and the basic is 25. Together, they're about 60 kilodalton. So the alpha designates the acidic subunit, and glutamic acid is mostly abundant in the acidic subunit, which makes the basic subunit more hydrophobic. Okay, so because you have most of your charged acidic amino acids in the acidic subunit, the other one is not as high and has high percentage of hydrophobicity, makes it the more hydrophobic subunit of the two. Quite a bit of homology in the sequences, and there's about 4 SS or 4 cysteine residues that can be linked or can be part of disulfide linkage. That means this bond is not necessarily one bond, it could be 2 bonds of disulfide linkages. So the monomers are arranged in trimers. So you have 1, 2, 3 monomers. That is a trimer. Each monomer is linked to the other by hydrophobic interaction. So the black line here designates a hydrophobic interaction. So the red is disulfide linkage, the black is hydrophobic interaction. And then each trimer is a hexagon because it has 6 individual subunits. But they associate, you have 2 trimers that they associate. So 2 hexagons or trimers arranged on top of each other. These dotted lines designates electrostatic and hydrogen bonding. Okay? So this is how complex legumin is. It is present as an oligomer. That means multiple subunits. And that's why the molecular weight can range between 300 to 400 when you add up all of these subunits together. And again, it depends on the variant or genetic variant of each subunit and how they differ slightly in molecular weight. Therefore, you have that range of 300 to 400 kilodalton. You do have some secondary structure, But mostly you have random coil, so you have about 6% alpha helix, 40% beta sheet, and a lot of random coil as a secondary structure. So when we run the soy protein on a gel, it will look really bad on an SDS gel. It will look like that. Lots of smearing because it's a large molecule or large molecules. So you won't be able to see the individual subunits. When you add a reducing agent, then you'll be able to see the individual subunits. These two here bands designate the acidic and the basic subunits of legumin. So, and we have different variants of the glycinin or the legumin of soy. So you have variant A3, A1, 2, and 4 chains of the acidic. And then we have the glycinin basic chain or chains around similar molecular weights. So here I don't necessarily want you to memorize the different grouping, but the idea here is that these groups have been identified and present in soy. So there are different variants within the legumin group. So you have the acidic and basic subunit. Within the acidic units, we have different subunits that are acidic. We have A1A, A1B, 2, 3, 4, and 5 that has been identified as genetic variants. And then for the basic subunits, we also have B1A and B1B, B2, 3, and 4. And these were grouped together because they share over 84% of homology within the sequence. They're very related, but some can be larger, some can be smaller than others. Group 2 also share 84% or greater of homology. But between the two groups, we have about 48% or less of homology. And that's how they were grouped. But this is nothing for you to memorize. It's just to show you that there are different variants, and that's why they are arranged. That's why when you see the gel, you don't see one band. There are multiple bands because each of these could have different constituents of the acidic and the basic, but they do share quite a bit of the amino acid sequence. And these also can be different within different varieties. Some varieties might have more of this, let's say, less of that, and so on. And that can impact also functionality. Vicillin, which is the 7S, it has also a sedimentation coefficient that ranges between 7.1 to 8.7. So the average is 7S, and that's why we use just 7S as a referring to vicillin. It has a molecular weight that is smaller than glycinin, 180 kilodalton, and it is glycosylated. So its surface is more hydrophilic. It has more hydrophilicity on the surface than glycinin has. And in this particular group, we rarely have any sulfur-containing amino acids. So we don't have disulfide linkages, we don't have cysteine. So this protein is not necessarily good for gelation. So keep that in mind. So again, it's rich in amides of acidic amino acid and low in arginine in general. So the way it associates, it's a trimer, and on average each trimer is around 60 kilodalton, and hence the 180 kilodalton of the molecular weight. And they are associated with each other via hydrophobic interaction. So it's less complex of an oligomer than legumin. when you run a gel, here they are. They look like they have larger molecular weight than glycinin, but glycinin, these are only the subunits. When they're associated together, they form 300 to 400 kilodalton. These range in these subunits of beta-conglycinin or vicilin. 7S beta-conglycinin is again in soy. So it has 3 different subunits, alpha prime, alpha, and beta subunits. And they vary slightly in their molecular weight, 72 kilodalton, 68, and 52 kilodalton is the molecular weight. Together they have around, on average, 180 kilodalton. So in soy, we have 3 vicilin types. One of them is beta-conglycinin, and it's the main one. But you do have gamma-conglycinin and basic 7S. But beta-conglycinin is the main vicilin in soy. So all of these subunits, the alpha prime, alpha, and beta, are mostly acidic polypeptides. But alpha prime and alpha are more hydrophilic on the surface than beta. Because of that, when they associate together, the beta subunit is mostly on the interior, and then the 2 subunits kind of cover the exterior of that oligomer. So beta resides in the core. We have similar homology or similar sequences, so they have high homology, but they could differ in cysteine, methionine, and tryptophan in this order. And they're highly glycosylated. All potential sites are glycosylated. Again, there were different species that were found of the beta-conglycinin. So you have trimers that have 2 betas and 1 alpha prime, for example, 1 alpha and 2 betas, or each subunit is different, alpha, alpha prime, or beta, and so on. Some are all homogeneous, so 3 alphas or 3 betas. So they can be a combination of any of those 3 different subunits to form the trimer. So what we'll talk about next is the association. I'll spend 5 minutes and give you a break. The association and dissociation, it's very important in soy because of the fact, or in general in legume proteins, because they are present as an oligomer. So there are conditions that will enhance association and conditions that will cause a dissociation. And these conditions, therefore, will impact whether the protein is going to gel under certain condition or is going to be more soluble than another set of conditions. So there's the association, dissociation. We'll talk about that. We'll talk about general solubility of the protein, the impact of pH, ionic strength is a big one for soy, and then heat stability and susceptibility to enzyme hydrolysis. So with susceptibility to enzyme hydrolysis, I'm not sure if I have a separate slide on this, but I just want to mention what I mean here is, given that it is an oligomer and a large molecule, this means it might not be as susceptible to digestion as another protein that is not a big oligomer. Okay? So and then the other thing is there are some enzymes that can hydrolyze certain subunits, some enzymes that won't hydrolyze certain subunits. So there is specificity of enzymes that are required in order to break down these subunits. However, if the protein is denatured, then it becomes partially denatured, not further polymerized, but partially denatured, then it becomes more susceptible to enzymatic hydrolysis. So partial denaturation in the case of soy protein or legume proteins that are large in molecular weight would be actually helpful to enhance digestibility. Okay, so let's talk a little bit about association and dissociation. So different factors impact association and dissociation. Ionic strength is one. That's the equation of ionic strength that takes into account the concentration of the ion and the charge of the ion and the different ions that are present in that salt. pH, temperature, obviously, protein concentration, denaturation, solvents like SDS or urea, and reducing conditions like presence of beta-mercaptoethanol or DTT for reduction of disulfide linkages. So, in general, when we have a 0.5 ionic strength, glycine exists as an 11S, mostly. If we increase the ionic strength, it starts associating more with other proteins due to shielding of charges and more hydrophobic interactions. And of course, this increases if the protein concentration is higher, then we tend to form a larger polymer with a sedimentation value of 15S. If we decrease the salt concentration, that means we have more water available for hydrogen bonding. Then instead of the protein associating with each other via hydrogen bonding, like we said, the trimer and the trimer associate via hydrogen bonding ionic strength, they will be interacting with water more, since now the salt concentration is less. Then it will dissociate into individual trimers. Obviously, increasing the pH or decreasing the pH also result in dissociation because of charges. They can break down even more into individual subunits if we have really high pH and really low pH reducing agent that will break the disulfide conditions. So, and this is a very old graph that I have to illustrate this. Somebody needs to draw it for me for extra credit. Anybody that wants extra credit, you can redraw this. That's what I've done in the past. You'll see several figures come out due to other students drawing it for me. Okay, so what happens here, this is around, this is the hexamer when you have the ionic strength of 0.5. That's your natural hexamer that is present. And then changing the pH and salt, reducing the salt concentration, increasing the temperature breaks hydrogen bonding and electrostatic interactions. So basically, this will result in trimers being dissociated. Extreme pH and reduced a little bit of denaturants like urea or SDS-PAGE then will break down hydrophobic interactions and give you monomers. The monomers you add a reducing agent, you break the SS, and then you get the two individual subunits, acidic and basic. Denature with denaturing conditions and reducing agents or temperature even, so these can be denatured, opened up. Without the reducing agent, but with heat, they can be denatured, heat or detergent, but still you have disulfide linkages. So it really depends on what the conditions are. You can end up with different outcome. So here it's just again reminding you that at pH 7.6 and ionic strength of 0.5, we have the hexamer, which is the two hexagons, trimer and a trimer. However, when we reduce the salt content, we interrupt the hydrogen bonding and ionic interactions because there's more interaction with water. Then we have the trimer. And then solvents such as urea and SDS can break further bonding. High acid conditions can result in also not polymerization, ionization and dissociation. And then the denaturation, glycine has a higher denaturation temperature than beta-conglycinin, just because it's stabilized by disulfide linkages. So this withstands higher heat, so it has higher thermostability than beta-conglycinin. For beta-conglycinin, it is a trimer under these same conditions. But then if we change the conditions under, you don't have to memorize that, but under these conditions it becomes a hexamer. So, all right, I'm gonna give you 5 minutes break, and we'll talk. We'll hopefully finish this and do the exercise set 5 together. Everybody here? We didn't give 5 minutes total. We didn't get to 5 minutes total yet. Okay. So let's continue. You've seen this before. I showed you to explain the SC before. But again, I just wanted to show you that the denaturation temperature of glycine and beta-conglycine are same as I have listed here. So glycine, which is the legumin, because it's stabilized by disulfide linkages, the onset of denaturation is around 92. Well, it varies a little bit depending on the variant. And then beta-conglycine is about 75. So these are separated fractions, a purified glycine fraction and purified beta-conglycine fraction, to confirm that this is indeed beta-conglycine and this is glycine. And as you know, this is a DSC that looks at the uptake of heat as you increase the temperature as an indication of denaturation. So solubility, it has a very typical bell shape where soy protein is in general soluble at extreme pHs and around the isoelectric point of 4.5, somewhere between 3.8 to 5, it's really poor in solubility, or even 3.5 to 5 is really very low in solubility. That's where you have minimal charge to zero net charge. And again, we have higher solubility under alkaline condition due to some amino acid ionizing at that condition, like tyrosine, for example, or cysteine could be ionized under high alkaline conditions, which increases the charge density of that protein. So I have recap questions from, I think I stopped here in one year, so, but you can review that on your own. This is very interesting paper. I have 2 papers here, maybe 3, that I found very interesting. Did very nice basic research on soy protein and how it's impacted by ionic strength as well as pH. So main finding of this paper is here in this figure, and then what they looked at is the impact of ionic strength and pH on the solubility of soy. And they did several testing, and they determined that, you know, in acidic groups within glycine, this is just the glycine fraction, acidic groups within the glycine or acidic subunits. You know, there's the acidic subunit and the basic subunit that forms the monomer. The acidic subunits they are more hydrophilic than the basic subunits. They, under the conditions of 0.5 ionic strength, they are 12 times more on the surface of the oligomer than the basic groups. So they are, the basic groups or subunits are within the interior of the structure, whereas the acidic subunits are on the exterior, under ionic strength of 0.5. With that in mind, we can look at the curve and say, okay, the square is when we have ionic strength of 0.5. So looking at the pH, so at low pH we have low solubility, and you go, why is that? Because the acidic groups are on the exterior mostly, and at low pH they're going to pick protons. So they're going to lose their charge because they're going to be protonated. So SOO minus groups will be SOOH. So the carboxyl groups will be protonated, no longer ionized. And because they are the dominating on the surface, not the basic groups, but the acidic groups, then the entire protein is less soluble under these conditions. As we increase the pH, the carboxyl groups start giving out their protons, then they become ionized. So we see a steady increase in solubility as we increase the pH. However, when we reduce the salt concentration, then we see that bell shape. When we reduce the salt concentration, now the exterior, we have basic groups dominating the exterior more. So they are more on the surface. So instead of being 12 times more for acidic groups on the surface, only 4 times more on the surface. So we have basic groups. So we have acidic groups, we have basic groups. Therefore, we follow the regular bell shape, where around the isoelectric point, we have less solubility, and away we have more charge density, because now we have more balance of acidic and basic groups on the surface. So if this shows up in a test, you'll be able to explain it, right? Okay. So another article did a really nice job comparing acidic subunits to basic subunits and the entire glycine. So they took glycine and they fractionated into acidic subunit and basic subunits and looked at solubility as impacted by pH to understand more the impact of structure on function. You can see I'm very fascinated by this paper, by these papers, because they did good science, unlike a couple of the papers we have seen in presentations. Not the presenter's fault by any means. Anyway, so the acidic subunit is this black square, and then the glycine, which contains both subunits, is the triangle. And here we don't have the 0.5 ionic strength, so it's not under the ionic strength condition that we saw in the earlier paper. So we do see that bell shape. It's probably lower than 0.5, but they don't report what the ionic strength is. So you see that bell shape. So we see the typical bell shape for glycine. But then, if we look at the basic subunit, it has really low solubility overall. So why is that? So we look at the amino acid composition. We find that the acidic subunit obviously is much higher in glutamic acid, and they don't differ as much by the basic subunits. Okay? But yet, because they differ a lot in the glutamic, this becomes more of a basic subunit than an acidic subunit. But what is more important is the basic subunit has much higher hydrophobicity. So it has 47% hydrophobic residues compared to 36% hydrophobic residue in acidic subunits. Even more, those that are highlighted in blue are the most hydrophobic amino acids: alanine, valine, leucine, and phenylalanine. They are present in much higher concentration in basic subunits than acidic subunits. So we have higher hydrophobicity and we have lower charge. So therefore, if we look at the basic subunit, it has 28% of its amino acid as valine, leucine, isoleucine, phenylalanine, the most hydrophobic. And it is a critical percentage. At this percentage and higher, hydrophobic interactions govern. That means even if we have some charge, but the hydrophobicity is so huge that the protein are really governed by attraction of hydrophobicity. So no matter what the pH is, the solubility is really low overall, whereas it gets even lower around the isoelectric point, or even your isoelectric point is really extends over a wide range here because of the dominancy of the hydrophobic interactions. Whereas the acidic subunits have 20% of the amino acid as these four, and it's below the critical concentration where proteins associate via hydrophobic interactions. So under these conditions, electrostatic interactions govern. So at high pHs, at high pH and low pH, you have more electrostatic impact rather than hydrophobic impact. So we can see a really good, tremendous increase in solubility. And then very sharp and narrow range of low solubility at a narrow range of pH. Okay, so now, the question that will is related a little bit to the previous paper. Why the acidic subunits and glycine have similar curve?
Are the basic subunits shielded by the acidic?
Yes, we said yes. We said earlier that on the exterior of the oligomer, you have the acidic subunits dominate the exterior. So since they dominate the exterior, they kind of govern the solubility of the entire oligomer. So that's why I like the paper. It's really good in linking structure to function. Okay. So this is another paper, not very exciting. I don't want you to learn any of this, these numbers, but it's also showing that even we talked about glycine, but also beta-conglycine, which exists as a trimer, also is impacted by ionic strength and pH, and the solubility is impacted under these different conditions. And the other important point I want you to know, not necessarily numbers, is that if it's a homotrimer versus a heterotrimer, how they could be different in how they are impacted by ionic strength as well as pH. That's all. But I don't want you to know numbers. Just know that there could be a difference of a homotrimer versus a heterotrimer, and pH and ionic strength impact their solubility. So soy protein is it's the most functionality, or not most functionality, the most applications used for their gelation and emulsification capability. So they're not really great. They don't have great solubility in acidic beverages, for example, because they have really bad solubility around 3.5 to 5.5. So they're not really soluble under acidic conditions. So they're not picked for acidic beverages. If they're incorporated, they would be in a blending with whey protein and at low inclusions. But they are good at gelation and they are good in emulsification. So for gelation, the gelation is dependent, obviously, like we talked earlier about gelation, it's dependent on the heat. the rate and the heating temperature. So the temperature and rate. Of course, protein concentration, pH, and ionic strength. So one of the best temp pH for forming a gel is the neutral pH. 7 to 7.5 is a good pH to form a soy protein gel. Adding a little bit of salt helps in forming aggregates at high temperature. So the thing is, if you heat at lower than 80 degrees, you get reversible gel. Why do you think? We just talked about the thermal stability of these proteins. Lower than 80. What is not denatured? Glycerin is not denatured. It denatures around 90 to 92 degrees C. So the interaction is mostly governed by hydrophobic interactions and glycinin, not glycinin, just hydrophobic interactions basically. It's not governed by unfolding and forming disulfide linkages. Just whatever hydrophobicity you have on the surface is governing the formation of gel. Remove the heat, hydrophobic interactions are weakened, so it is a reversible gel. However, if we heat at higher than 90 degrees, like say 100 degrees, we're denaturing the protein, we're opening it up, we are allowing disulfide interchange, therefore we are allowing not only hydrophobic interactions and water-protein interactions, but we're allowing for disulfide linkages as well to stabilize that gel. So heating temperature is really important. Of course, the rate is very important because we talked about the rate earlier. If you are heating at a high rate, then you're forming aggregate and precipitation. You're not giving the gel time to form the three-dimensional network. So it starts with forming soluble aggregates, and with high concentration of protein, you start forming the network. If you don't have enough concentration of protein, you just form soluble aggregates or insoluble protein subunits. So that's why with soy protein, you need about 15% protein to form a good, strong gel. Whereas a different type of protein, you need much less. Let's say meat protein or gelatin, you need much less than 15%. Okay. So if we take out beta, you have a question?
She's asking was 1.5 or 5.0?
15, yeah. So if we split them apart, the glycinin fractionated from the beta-conglycinin, and we try to form a gel with beta-conglycinin, it's weaker because it doesn't have disulfide linkages. And also because it has a high amount of glycosylation, so you have more hydrophilicity, you don't have a lot of hydrophobic interactions. High acidity on the exterior, no disulfide linkages, that would make it a weaker gel than glycinin. Therefore, best gel is really a mixed system with glycinin and beta-conglycinin, but with a greater ratio of glycinin to beta-conglycinin, you get a better gel.
I think that maybe you touched on this, but would heating at a faster rate create a stronger gel?
They would aggregate and expel water, so they will form aggregates and precipitate.
Okay.
The high rate is that you're denaturing them so fast, they're moving to interact with each other so fast, there's high kinetic energy. So they're forming aggregates rather than soluble aggregates, they're forming large aggregates and precipitate. The formation of a gel has to start with soluble aggregate. Okay, so the ratio is very important, and higher glycine to beta-conglycine ratio gives you a better gel. And also the subunit species play an important role in terms of the subunit molecular weight and the subunit's amount of cysteine in these subunits will impact the gelation. Here's going back, I don't know if I showed this before, I probably did, but here going back to demonstrate the impact of the specificity of enzyme hydrolysis. And if we break down certain subunits, how would the gelation be impacted? That's again a confirmation that glycinin is important for gelation. So this is an example. So this is soy protein here, and here we have a hydrolysate where we use pepsin. So pepsin has specificity to the glycinin subunits. So when we hydrolyze with pepsin, you see no glycinin subunits. They're broken down into small molecular weight soluble peptides. And then the beta-glycinin is intact. And then here, when you use papain, this is both the SPI, soy protein acid. When you use papain, you will see that they don't have any more beta-glycinin because papain is specific to beta-glycinin subunits, so it broke it down and resulted in soluble peptide. So how did that impact gelation? So reduced conglycinin hydrolysate, RCH, reduced conglycinin hydrolysate, reduced glycinin hydrolysate, and the control. So the control had a decent gel strength. When we hydrolyzed the glycinin, so reduced glycinin hydrolysate using pepsin, the strength of the gel was reduced because now we have small peptides broken down, they don't form good gel. When we reduced conglycinin, the reduced conglycinin hydrolysate, it did not, either it improved a little bit or was not really very different. So the conglycinin did not have an impact on the strength of the gel. So this is proving that glycinin is the driving force for gelation in soy protein. So another, I think this is something done, I can't remember where I got this data, from some past work in our lab. But anyway, here we're looking at emulsification. And if you have higher beta-glycinin in there, so that means lower glycinin to beta-glycinin, you have better emulsification. Because beta-glycinin has higher surface hydrophobicity and better balance between surface hydrophobicity and hydrophilicity than glycinin, and it has a lower molecular weight. So with lower molecular weight, even as a trimer, it can get to the surface faster, or the interface, faster than a larger molecular weight. Because of that, the smaller size gets to the interface, more of it would be forming a thicker film, and therefore we have better stability as well. So we have better hydrophilicity to hydrophobicity ratio or balance. We have smaller size in beta-glycinin, and we have higher surface hydrophobicity. What I have here is just to show you what we normally see when we have casein, sodium casein. Usually have the best emulsification capacity. That means the amount of oil that can be emulsified by a certain amount of protein. Soy protein tend to be better emulsifier than whey protein isolate. Very quickly, these are the different soy protein ingredients in the market. We have the soy flour, soy protein concentrate, soy protein isolate, and this is how they differ in their composition. So soybean is really high in protein. Once we defat, remove the fat. The fat now is less than 1%. Obviously, we increase the all other composition, but specifically soy protein becomes about 50% protein. And then when we concentrate even more using alcohol, getting rid of small sugars and oligosaccharides, we get 65 to 80, on average 70% protein, When we use alkaline extraction, we're getting rid of soluble sugars as well as large carbohydrate, dietary fiber specifically. Then we end up with higher protein concentration. These are different uses. So soy flour can be used for meat products and baked good, as well as texturized meat analogs. But it does have a beany flavor since it was not subject to any processing, really, and removal of flavor notes. And it does have your oligomers that are insoluble, raffinose and stachyose. Not insoluble and not digestible. Soy concentrate, it has less beany flavor because that has been treated with alcohol extraction, and we have less indigestible carbohydrate because the oligosaccharides have been removed with the alcohol treatment. And soy protein isolate has the cleanest flavor. It doesn't have your high concentration of sugars or oligosaccharides or fiber, and flavors have been removed during processing. This is the general processing scheme for soy. So you start with the beans, and then cleaning and cracking, so you can remove the hulls after cracking, and then you get the soybean chips here, and then some conditioning, temperature conditioning and moisture, and then flaking. You can roll them and flake them, and then after having the flakes, there is a step here that are not included, is you press the flakes to extract most of the oil, and the remainder of the oil you use hexane extraction to remove the rest of the oil, and then you want to remove the solvents by drying, desolventization, and then you get defatted flakes. They can go in different routes. The defatted flakes can be ground into soy grits and further grinding into soy flour. Or the defatted flakes can be subjected to protein extraction. So we can use the alcohol extraction of sugars, and then drying, you get your soy protein concentrate, or the alkaline extraction and precipitation by isoelectric pour precipitation, neutralization, drying, you get your isolate. Your concentrate and the flour can be fed for extrusion and texturizing, and used for texturized products, meat analogs. This is you've seen before, the different steps, alcohol versus protein extraction with alkaline. If you want to produce tofu, for example, you start with your whole soybeans, you soak and ground, you get the soybean slurry, you heat it to activate trypsin inhibitor, filter, get the okara out, and then you get your soy milk. The soy milk can be treated with coagulant, so there is a calcium there to promote gelation, and then pressed, pulled and cut, and you get your regular tofu, and the residue is soy milk whey. You can texturize either using soy flour or concentrate. You mix it with water. Sometimes you add other ingredients like fat, for example, or starch. And then it goes through the extruder. The pressure of the die that makes it expand and create a spongy meat-like structure. And you get your texturized meat-like product that get cut and shaped and dried, cooled, and packed. Okay, this is the nutritional value very quickly. It has high nutritional value, PDCAS-1. So, and it's low in fat, which led to that claim of 25 grams of soy protein a day as part of a diet. Low in saturated fat and cholesterol may reduce the risk of heart disease. FDA wanted to remove that claim, but there was backlash from industry not to remove that claim. So I don't know where it stands right now, but obviously they need many more studies to prove or disprove it again. Other health benefits: decreased risk of breast and other cancer, prevent osteoporosis, and it has isoflavones, which are phytochemicals, are associated with soy protein, and they have other physiological benefits. So soy protein is great, except it's GMO and allergenic, but yeah. That's it. We have 10-15 minutes. I want you to spend some time on the exercise 5. So you can separate in groups of 2 again and spend 10 minutes, and we reconvene for 5 minutes at the end. You can turn around any minute now.
You said groups of 2.
You wanted to
Groups. 2 groups.
I was like, oh, different this time.
Yeah?
Are we supposed to so the major protein fractions are like casein and weight?
Yes.
Are we supposed to do casein and weight information all the way down, or the subunits of each?
So for protein components, what would be the components of casein? What would be the components
Like molecular weight, should we list?
for each?
Okay.
Yeah. You want to describe each going forward. Yeah.
Should we split up one group does soy and one group does milk?
Oh yeah. Let's do that. You want to do whey?
Yeah.
Do soy. That's a good suggestion, Kate.
Is it more than 60 kilodaltons?
For which ones?
For the casein. I know for whey protein, beta lactam is 18 kilodaltons, alpha lactam is 12 kilodaltons. And it's in
Yeah, I don't know about for each subunit.
They ask. Can I ask about the difference about protein fraction in calculation?
Yeah.
Okay, so what are the different types of proteins here, and within each group, and what are the subunits?
Okay. Oh, thank you.
Yeah, that one we can skip.
Conference for glycine and alpha 1.
That's a lot. Yeah.
No, I think I'm sorry. No, it's been it's 6 molecules. So like, yeah. So we try that control.
Then DSA is 65 kilodalton. That's the third fraction.
Is it just 65?
Yes, 65. DSA alpha S1 is 23 kilodalton. Alpha S2 is 25 kilodalton.
Oh, hold on. It's just within your
Alpha S1 is 23.
Oh, yes.
S2 is 20. Beta is 23, 93, which is 24.
Wait, beta is what?
23, 90, you were right, it's 23 and 24.
Yeah, 24. That's
Kappa casein is 19.
BSA was 60.
Yes.
Yeah. It's a very, very it's just for,
Okay, let's come back together as a group for the last 3-4 minutes, for only 3-4 minutes. All right, we'll start with this group. What did you get for milk proteins? Major protein fractions. Whey and casein. What's the percentage distribution?
80% whey, or sorry, casein, 20% whey.
Good. What about protein components for casein?
Casein has alpha, alpha S, alpha S1, alpha S2, then beta, kappa casein.
Okay, and whey?
Beta lactoglobulin, alpha lactalbumin, BSA, and immunoglobulins.
Yeah. But the major ones are really what you want to focus on going forward is beta-lactoglobulin and lactalbumin. Okay, molecular weight. What did you guys come up with? You have numbers?
Yes, so
Okay.
beta lactoglobulin is 18 kilodalton, alpha is 14 kilodalton, PSA is 65 kilodalton. Then for casein, alpha S1 is 23, alpha S2 is 25, beta is 24, kappa is 19.
Very good. I did a mistake. But yeah, you're correct. Okay, molecular association and forces. So, how is the casein associated? Somebody else, Katie?
It's a live cell. It has hydrophobic interactions with calcium phosphate, which is
Yes, and what stabilizes its micellar structure? Yeah.
oh, I don't remember, but I hydrophobic.
What stabilizes the structure so the micelles don't bind to each other? The very kappa casein structure. Yep, the glycomacropeptide. All right. What about whey proteins? Do they associate? Huh? Yeah, it is globular, but do they associate into quaternary structure? They could be monomers, they could be dimers, that's a quaternary structure. They could be octamer, depending on the pH. Okay. What are the predominating amino acids? In casein?
Protein.
Protein. In whey? What did you say? Lysine.
Lysine.
What else? I don't know why I have leucine. I have leucine. Not sure about why. But dominating, you have sulfur-containing amino acids. Presence of conjugated proteins. Do we have any conjugated proteins in casein?
Phosphorus.
We have phosphorylated alpha and beta, and we have glycosylated kappa. Do we have any in whey? No. What taste? What does casein taste like?
Hay.
Huh?
Hay.
Hay?
Those are off flavors.
Huh? No,
Creamy.
dating.
Okay.
Whey is cleaner taste. Color, what's the color? Well, calcium caseinate is opaque, whereas if we talk about sodium caseinate, I don't know, it's not. I mean, the powder would be white, obviously. So heat gelation is casein known for thermally induced gelation as a functionality? No. If you want to go, you can go. I can post this online. Otherwise, we can continue. Up to you. I can continue for a couple of minutes, or just let you go. Your call. Okay. Emulsification. Which is a better emulsifier? Casey, you want to explain that because it has a highly amphiphilic structure, open and flexible. Whereas whey protein, you need to denature it, partially denature it for it to become an acceptable emulsifier. Can it be texturized? Potentially. Can. It's not really used for that purpose, but yeah, you can. Okay, quickly, soy protein, what do we have? What are the components? The protein fractions. We just talked about them. Glycine and beta-conglycine. Okay. It depends on the cultivar, which one is the major one. So I didn't put a percentage because percentage can vary based on the cultivar. All right, so what are the protein components within beta-conglycine? What are the subunits? Alpha prime, and beta. In glycine, we have the acidic and basic subunits. These are the basic subunits that associate to the bigger molecules. Okay, molecular weight,
Glycine around 300, 400, and beta glycine 150 to 200.
so molecular association,
Within the monomers is specified linkage. Within the between the monomers is hydrophobic,
yeah,
and between two hexagonals is electrostatic and hydrogen bond.
perfect.
For beta-glycine, it's mostly hydrophobic interactions.
It is hydrophobic interactions, and you have homo or heterotrimers.
Yeah.
Predominating amino acids,
For glycine, it's acidic amino acids and arginine.
mm-hmm.
And for beta glycine, again, amines of acidic amino acids.
And there are hydrophobic residues in both, really high percentage. Do we have conjugated proteins? Beta-glycine and all potential sites are glycosylated, glycine rarely glycosylated. Taste could be beanie taste, less taste with more isolation, with more purity. You want to say that. Color, off-white. Gelation, heat-induced gelation.
Yeah, glycine is the driving.
Yeah, glycine is the driver, it has better gelation ability than glycine due to less glycosylation, less exterior acidity, but overall soy protein has good thermal gelatin. Emulsification, beta-glycine. We have the better hydrophobic hydrophilic balance, smaller size. Yeah, but for both, you want to specify that the ratio of glycine to beta-glycine is an important determining factor. And texturization is very good for texturization. Texturize soy protein concentrates using extrusion is very common. All right. Good. So please turn this in next week for extra credit.